Academy of Sciences for giving me this opportunity. It's an honor to be here. So I'm going to talk about what I do my current research on primarily, and then towards the end I'll talk a little bit about the other topics that I work on. And the primary topic that I work on that I'm very interested in exploring, and there are really like a plethora of questions to try to answer in this area, are combinatorial games. And I, being a probabilist, I study them on random graphs, okay, so random structures in general. So I did my PhD, so I'm not that old, so I did my PhD in 2017, completed my PhD in 2017, so I thought I would just start with the premise there that my doctoral thesis, this focused on studying graph properties that can be expressed in terms of first order logic or existential monadic second order logic on random graphs. So look at these properties that can be expressed as sentences in this particular logic. And then I study the probabilities of these sentences holding true on certain classes of random graphs. So looking at Ayer-Dishronai random graphs, looking at Galton-Watson trees. So I'll come to some of these random graph models in a bit. So since then, random graphs have formed a fundamental object of interest for my research in general. And random graphs, I think nowadays pop up in everything. So they are the go-to models when you want to model networks of any kind. So it could be social network, could be electrical networks, could be biological networks. So, and as I was saying, so the most fundamental, I guess, the most primitive model of random graphs were the Ayer-Dishronai random graphs proposed by Paul Erdős and Alfred Renai in their 1960 seminal paper. And they're still very useful, but of course we have branched out. We now have other kinds of random graph models, like the geometric random graph models. We have random graphs that are used for modeling community structures, like in clustered networks. So for example, we try to have these, so we use regular stochastic block model or stochastic block models in general for trying to model clustered networks where there are communities present. Okay. So random graphs kind of show up everywhere, and there are various ways of studying them, various angles from which we can approach them. I do try some of these angles. One of the favorite ones is working on two-player combinatorial games on random graphs. So because I'm very interested in combinatorics, so they are interesting by themselves. Trying to understand both strategies as well as probabilities, because we are playing these games on random graphs, so there is always probability involved in all the questions I address. But these games are also useful because they do have certain very fascinating connections with topics in both physics and theoretical computer sciences. So in physics, for example, percolation and statistical mechanics in particular, that I have seen. There are probably many more connections that I don't know of, and I'm trying to learn. And then in theoretical computer sciences, something that I come across again and again in my research is automata theory. And in particular, I have encountered now probabilistic cellular automata and probabilistic tree automata. So cellular usually refers to the automata being defined on some lattice structure, on infinite lattice graphs, and tree automata on trees. So a two-player combinatorial game, so what is it? It's a perfect information game. So what does that mean? For me, what it means is that since I'm playing this on a random graph, what do I do first? I take the random graph model, I simulate a realization of the random graph from this particular model, and this realization is now a deterministic graph. It came from a random graph model, but now it's a realization, so it's a deterministic graph. It is revealed in its entirety to both the players, and the players can. I usually assume, but although it doesn't sound very practical, but it does simplify a lot of mathematical work for us. I assume that the players have infinite foresight. They kind of can really foresee all the strategies that can be used against each other. The questions, as I was saying, that I'm usually interested in are basically trying to understand the probabilities of the various possible outcomes of these games. So what are the three possible outcomes usually? Usually there are three outcomes. First player winning, first player meaning the player who makes the first, plays the first round, makes the first move in the game. First player losing, and in some cases there is also the possibility of draw. Draw meaning the game will continue indefinitely forever and neither player would be able to achieve a desired outcome. And I try to understand the probabilities of these various outcomes depending on the random graph model that I'm working on. Sometimes I'm interested in trying to figure out winning strategy, at least one winning strategy for one particular player. And this is of particular interest when the players' roles in the game are asymmetric. So there are some games, I can throw some of the names in here, even though I'm not going into the details. So some games such as normal game, IISER games, the game that I will talk about primarily here, percolation games. In these games, the players' roles are symmetric. But then there are some games, such as make or break or positional games. These are a very popular class of games in which the players' roles are asymmetric. So there are many applications of combinatorial games, but since I started with mathematical logic in the very first slide, I just want to mention one of the first applications that I encountered, thanks to my doctoral advisor, Professor Joel Spencer, introducing me to this class of games. So there are something called the Ehrenfeucht-Frasse games. Often we shorten the name and just say Ehrenfeucht games. These are used to check if two given structures or two given graphs are elementarily equivalent. What does that mean? That means that if you take, there is a notion of quantifier depth, which is involved with first order logic. So let's say that you have a given quantifier depth, it's a positive integer, some k, okay, so it could be 10, for example. And you look at all possible first order sentences. These would be some graph properties, some local graph properties actually, of quantifier depth, let's say 10. And now you are asking, so you have been given two graphs by somebody. When you ask whether these are elementarily equivalent in terms of these sentences, what you're basically asking is, if you take any such sentence, let's say A, does it hold for both the graphs or does it fail to hold for both the graphs? If it's something like that, then you say that these two graphs are elementarily equivalent. And one of the ways of checking whether two graphs are elementarily equivalent is by playing these Ehrenfeucht-Frasse games on these graphs. Okay? There are two players involved, spoiler and duplicator, and if the duplicator wins the game, again, not going into the details of this, then you say that these two graphs are elementarily equivalent. The similar questions can be answered in other, not just first order logic, but any other class of logic, any other class of logical sentences. So today I kind of want to dwell on percolation games since these caught my fancy since 2021, and I have been trying to delve deeper into this. And it's just absolutely fascinating because they tie in so closely with the notion of percolation in physics. And so what's the notion of percolation in physics? I guess a lot of people here already know, but I'll just say it for the sake of completeness anyway. You have usually an infinite graph, but it probably doesn't need to be infinite. And in this graph, certain edge, so every edge is open with a certain probability and closed with a certain probability. And you have the notion of a source and the notion of a sink. And you're basically thinking of a fluid that is starting from the source and flowing towards the sink, but it's not able to flow through any of the edges that are closed. So is there a path for the fluid to go from the source to the sink? This path has to consist of only open edges. Can you find such a path? This is the primary question of percolation. And in case of percolation games, see, I was talking about flow of fluid here, and the fluid is the fluid and this random graph that we generated by assigning open or closed labels to the edges. There is no notion of adversary involved. But what happens if you do bring in the notion of adversaries? If there are two intelligent agents trying to do this thing where they're trying to find a path from the source to the sink, what happens in that case? So this adversarial nature is what makes the games really interesting and really different from just the processes. So in a percolation game, you have some directed graph G. I usually consider infinite lattices or infinite rooted trees. So every edge is labeled a trap with some probability P. So P is of course between 0 and 1. It's labeled a target with probability Q. So it's labeled safe or open with the remaining probability 1 minus P minus Q, which tells you that P plus Q is less than or equal to 1. And the game is as follows. So it involves 2 players. As I said, these are 2-player combinatorial games. And there's a single token. And the whole point is basically moving the token. And directed graph means that you will move the token along the directed edges. Now the token will start from some initial vertex, which we refer to as the origin. And these 2 players will take turns to move the token. So if the token is at some vertex U of the graph G, now whichever player's turn it is to make a move can move the token from U to a vertex, any of the vertices V in G, such that the directed edge UV is in G, okay? So there is an edge that leads from U towards V. And this from U towards V, this notion comes from the directed nature of the graph. How do you decide the outcome of such a game? A player loses if, I should have written a player wins, I'm sorry about that. Player wins if she's able to move the token along an edge which has been labeled target, or she's able to force her opponent to move the token along an edge which has been labeled a trap. This is the basic understanding. I'm really sorry about missing that. A player wins, that's what I meant. And I studied this on 2 different settings. The first one is this class of random graphs that are basically rooted random trees called rooted Galton-Watson trees. So what are these things? Just to give you a very one-line introduction to this. This model was proposed by Francis Galton and Henry Watson, I think 1875. I don't remember the exact year. But the whole idea was they were trying to model the dwindling of aristocratic family lines in the UK, or back then I guess it was not the UK, but Great Britain. And they proposed this very simple model of a tree where you have a root, which is the original vertex, and then it gives birth to a random number of children. This random number follows a distribution that is referred to as the offspring distribution. And then these children, each of them independently gives birth to a random number of children according to the same offspring distribution, and so on. This continues. And their question was always to try to answer when there is a positive probability of the tree surviving forever, and when it is almost surely going to die out and be a finite tree. So I played this game, this percolation game, on such rooted Galton-Watson trees. And I guess, as I said, the whole point is to try to find probabilities of various possible outcomes of the game. And what we end up finding is that, so if I let W denote, so W, P comma Q, because it has a dependence on these parameters P and Q with which you mark the edges, trap, or target. So if I let W be the probability of the first player winning, then a certain nice centered and scaled version of W equals the minimum positive fixed point of a certain function. This function I haven't dwelt on because the technical part doesn't matter. This function depends on PQ and something called the probability generating function of the offspring distribution. And usually you don't get explicit expressions for these probabilities. You do get them as certain fixed points of certain functions. And then you analyze those functions to glean as much information as possible about these probabilities. The interesting thing, so you also get some similar results about the loss probability for the first player. But the interesting thing is this, the last thing. We show that the probability of draw in this game, on this percolation game of rooted Galton-Watson trees, is 0 if and only if this same function that we saw here, it's written in this weird manner because it's the composition of the same function with itself, GPQ with itself. So that's why I wrote a 2 as a superscript. This function, if and only if it has a unique fixed point. So if and only if it has a unique fixed point, the probability of draw in this game will be 0. So by analyzing the function, you get to know if the probability of draw is 0 or not, if you can analyze the function, if it's simple enough to analyze. And why are we interested in the probability of draw? Because you see that there is any possibility of draw only if you can find, let's say the token is initially placed at the root of the tree, only if you can find an infinite path from the root, starting from the root, which comprises entirely of open or safe edges. Okay, and this ties in with percolation. Immediately you know that for draw to happen, an infinite percolation cluster has to exist. So and I just wanted to mention that for when you take the offspring distributions to be some specific distributions like binomial, these are like very popularly studied distributions in probability, in discrete probability. So binomial, Poisson, negative binomial. You actually can find very neat expressions for the regimes, depending on P, Q, and the parameters underlying these distributions, where the probability of draw is 0. Okay, so for example, when it's binomial d comma pi, whatever that means, so there are like a bunch of parameters involved in these distributions as well. It's a very neat condition. So this inequality has to hold, and if it does, then the probability of draw is 0. So you can actually check it like in 2 seconds. Okay, when it's Poisson lambda, again there's this parameter involved. Then this inequality has to hold, and if it does, then the probability of draw is 0. So this kind of stuff is what we call, at least we refer to as phase transition phenomena. So when I was listening to Professor Umesh Wagvar's talk in the morning, he was talking about this germanium antimony tellurium and how it undergoes like this amorphous to crystalline phase. I think that would be referred to as a phase transition phenomenon. Okay, and phase transition phenomena are so like of interest to probabilists and people who study statistical mechanics. So and I'm interested in these two, and this kind of, so once this inequality is no longer true, then there is a phase transition that happens, and the probability of draw goes from 0 to positive. That's what we refer to as phase transition. Okay, there's a transition of the phase. Okay, and a similar question we tried to answer, but it couldn't answer in its entirety. Partial results on the two-dimensional square lattice. So here, you can move the token from where it is currently located, let's say xy, where x and y are integers, to one of its neighbors, either x plus 1 comma y or x comma y plus 1. And in this case, we show that whenever the probability of trap and target, P and Q, they satisfy these inequalities, the probability of draw in the game is 0. Okay, but simulation tends to show that this should be true whenever P plus Q is strictly positive. How am I doing on time? So 2 minutes left? Okay. So I just want to mention that this kind of questions, the instance of draw, whenever we are focusing on the instance of draw in this kind of games, it ties in very closely with something called ergodicity of probabilistic cellular automata or probabilistic tree automata, whichever structure you are studying the game on, whether it's lattices or trees, that's what it depends on. And ergodicity is always of interest to us because it helps with numerical computations a lot. If something is ergodic, especially for probabilistic cellular automata, you get a Markov chain, and as long as that's ergodic, it helps with numerical computation. So we are interested in questions of ergodicity. It also relates very closely with spatial mixing properties in models of statistical mechanics. Since I don't have a lot of time, I don't want to go into too much detail about this slide. In this slide, I was just going to talk about another kind of percolation games where you mark the vertices of the graph, either trap or target or open. Okay, not the edges. And here we actually do have a complete result. We are able to show that the percolation game that we were considering, and this is a very recently accepted paper and a very favorite one of mine, the probability of draw is 0 whenever P plus Q is strictly positive. Okay, so that's a very stunning result in the sense of like how fast this phase transition happens. I just wanted to mention that, why are we interested in probabilistic cellular automata or probabilistic tree automata? Because they have countless applications. When I was writing this paper, I was looking into what kind of applications these have. And since this is a very mixed audience, they have so many applications in modeling systems in physics, chemistry, biology, They have applications in dynamical systems, in computational cell biology. They have applications in combinatorics, in statistical mechanics. I even found this paper that talks about modeling astrobiological history of the Milky Way using cellular automata, which is, to me, it's like amazing. So we are interested in knowing more about these objects. And okay, I'm going to end here that ergodicity is a question that comes up very much in my research and is of primary interest to me. And I wanted to talk about that. And thank you again for giving me the opportunity.
I have actually three basic questions.
Huh. Maybe I'll come closer because I cannot hear you.
The first one is,
yes.
Do you consider your random graph approach to certain problems as anything to do with the game of chess in which the two fellows choose random sort of patterns, as it were, in their choice of moves?
But that is what.
I'll spell out the question so that you can answer.
Oh, yeah, sure.
The second one is, do you consider the chess game as a non-zero-sum game or zero-sum game?
Okay.
Third one is, what is the order of complexity involved in trying to come out with the random graph approach to a chess situation, let's say end game situation?
Okay. So first of all, when we think of chess as such, it's not a combinatorial game. So I only focus on combinatorial games where the players are basically like gods. They can see everything. But in chess, I mean, the practical applications of chess, I guess that's not true. So I'm not sure about this the zero-sum approach, and I don't actually know like whether chess is played with this kind of random moves, like because. Correct. But yeah, I have actually no idea whether like how that connects with this, because this is, and chess is also, like I said, it's not a perfect information game. Yeah, so you would not be able to really read your opponent's mind, and you probably won't be able to see how the game can unfold, like several moves from now. Even a computer cannot. So that behaves very differently from this game. Yeah, in general, that would be and I actually don't know about the complexity answer. Like no, no idea at all. Yeah. Thank you.
You talked about the probability for draw being zero in certain circumstances, and then one of the two players has a winning strategy. But do we get any information about how easy or hard it is to find these strategies? Some representation of the strategies?
Yes, some sort of algorithmic question, right? So I don't really deal with that, but I don't think it's that easy always. Like usually the questions that are answered, now that could be because only people are interested in only that part of the existence of a strategy, whether that is true or not. For example, the question about understanding logic on random graphs, again, it's always about whether there exists a strategy for the duplicator. But I don't think finding such a strategy would be easy. At least when I was proving the existence, I was already kind of like, wow, there's so many different cases to consider and this and that. So I don't think that it would be that easy. But yeah, again, complexity questions, I don't know. Sorry.